Okay, so here's the rough snow or ice. The sled starts off with an energy EI is equal to 1/2 mv squared. It slides for some distance d, and it comes to a stop. V final is equal to 0. There's a coefficient of kinetic friction mu sub k. So when in doubt, draw the force diagram. There's the mass. There's the perpendicular force of the surface pushing upward. There's mg pulling downward. And then there's the force of friction, force of kinetic friction. That's equal to mu sub k times this perpendicular force. Now obviously, if we're moving in this direction, these two forces are not going to do any work on this mass because they're both perpendicular to the direction of motion. Okay? This is the delta R that we talk about, the displacement. So these don't do any work, and since there's no acceleration in the vertical direction, these have to be equal and opposite to each other. So we can immediately write that the absolute value or the magnitude of F perpendicular must be equal to mg. So we could write this as equal to mu k times mg. Right? And of course that force is going opposite the motion. So since this is a constant force, since we're going in a straight line, we can just write that the work done by this external force is equal to the magnitude of Fk times the magnitude of delta R times the cosine of the angle between them. That's going to be equal to mu k times mg times the distance that we moved, and the cosine of the angle between them is 180 degrees, right? Because the object is moving that way and the force is going in that direction, so they are opposed to each other. Those two vectors are anti-parallel. This becomes a -1. And so the work external is equal to mu k times mg d, and I've got to put a -1, and that's equal to the final energy of the mass minus the initial energy. Okay, the final energy is going to be 0, and the initial energy is equal to 1/2 mv squared. So this is 0 minus 1/2 mv squared that we started off with. And if you remember, this initial energy that we calculated here from the previous argument was equal to mgh. That was the energy we had at the top of the hill. I mean, that was the amount of work done by the forces going down as it went down the hill, produced this kinetic energy, and so we get this. So let's see how we can write this out properly. I've got minus mu sub k mg times d is equal to minus 1/2 mv squared, where v is the velocity when we hit the rough patch. Notice that the m's are going to cancel out, and I should get that d is equal to v squared, the initial velocity, over 2 mu k times g. Let's see if I did that right. So this is equal to that. There's the v squared. There's the 2 comes up. There's mu and the g. All right, so that's the distance that we slide before we come to a stop. All right, so that's an example of how you would use energy as changes in energy as work done by an external force.